Okay, let's talk about radicals this time. So your two goals for radicals are going to be 1, understand basic radical mechanisms, and 2, you got these really cool relative yield problems that they're going to want you to be able to solve. So how do radical reactions take place? The most common way you'll see them is you'll have some sort of halide or halogen like Br2, Cl2, one of those guys, and then there will be some light that is usually ultraviolet shown on this. So when we shine that ultraviolet light, what happens is what we call homolytic bond cleavage. So the reason why we have these half arrows or fish hooks is because this bond, instead of transferring like we usually do where you see both electrons move, instead one electron will move over here and one electron will move over here. And what you'll get is 2 bromine radicals, and this is called initiation. Now, when does this H-nu thing work? Well, typically when you have a bond that is perfectly covalent, like this one, that will allow the light to cleave it homolytically. So you need the same electronegativity on both sides for this to usually work. Okay, so what do we know about radicals? Well, you could pretty much treat radicals like their carbocations with a few exceptions. So tertiary radicals are more stable than secondary radicals are more stable than primary radicals. And that is for the similar reason to carbocation intermediates. Radicals are electron deficient species, but not to the same extent that carbocations are. So even though tertiary is better than secondary is better than primary, the energy gaps between these is much less. So primary radicals aren't that incredibly unstable, unlike carbocations. So you can't have a primary carbocation, but you can have a primary radical. That is far more common to have. Let me just... Okay, the other thing is that when we're talking about this initial initiation step, fluorine is highly reactive when it is a radical. So fluorine will usually cause explosions, so that's why we don't use it. When we try it on chlorine, we get low selectivity. So for chlorine, the energy difference between the tertiary, secondary, and primary is very small, so you'll actually see a lot of different products once we start doing radical chain reactions. Bromine has high selectivity toward the most stable radical, and iodine is unreactive. So you can actually get iodine to do this homolytic bond cleavage. Okay, so let's take a look at an example of a radical mediated reaction. So here we again have that Br2 in the presence of ultraviolet light. That's what this HV, it's actually supposed to be a nu and H-nu, because if you've taken physics, then H-nu is your light. Okay, so the initiation step is exactly the same as above. You have the light shine on this bond, and that'll cause it to homolytically cleave into 2 radicals. Afterwards, we have the substrate, and we have the radical. So the first major way that you'll see radicals interact with, I guess, organic molecules is through this pathway. So here we have this radical. Okay, so the other thing you need to know is that these fishhooks will always be starting at a bond, which is kind of weird. So this bond will break up, and one radical will go here, and the other electron will go here, and forming a bond with this bromine radical. So what's actually happening here is called hydrogen abstraction, which is when a radical, I guess, bonds to a hydrogen, generating another radical. So here we see the bromine radical attempting to bond to this hydrogen right here, which will in turn generate the radical at this location. The result is this. So you generate a new radical, and you have HBr now. So this is called a propagation step. So propagation is any radical step that generates more radicals. So over on the left we have a bromine radical, and over on the right we have a radical substrate. So note that most stable radical was formed through abstraction. So we had the choice to take any of these CH bonds. Any of these CH bonds on this substrate are reactive to radicals. But since we have a bromine radical, that is pretty selective toward the most stable radical formation. So we are going to attack this tertiary CH bond right here and generate a tertiary radical. Okay, now that we have that done, what can occur is the attack of this radical on this bond, initiating another homolytic bond cleavage. And the result of that will be the generation of our desired product, and we have another radical. So this is another propagation step. Okay, and if we want the chain reaction to end, one possible way for it to end is if we have these radicals add together and generate this. So termination is the loss of a radical. So here we had two radicals combined to make a non-radical species. That's a termination step. Note there are many possible terminations. This is just one of the possible termination steps. If you don't have any termination, well, it just means that you have an ongoing radical propagation. But eventually, if you generate enough radicals, they're going to do what they did here and create a non-radical. So this is a recombination. Okay, so let's summarize all the information that was just presented. So radical reactions have three major steps. The first step is the initiation. Initiation is when you first introduce radicals into your system, often through the ultraviolet light. The second is the propagation step. This is when you have the steps that you need to generate your product. Typically, there's multiple propagation steps. You could have only one though. So the requirement for a propagation step is that a radical generates a new radical. And lastly, a termination step is when radicals combine in some way to generate a non-radical. So if you're ever stuck trying to predict the mechanism of a radical reaction, there's a few common pathways that these proceed down, a few different ways that radicals will react. The first one is the one we saw first, and that is hydrogen abstraction. So that occurs when a radical targets an H, giving another radical. So that's what we saw over here. This bromine radical targeted a hydrogen, abstracted it, generating another radical. So this is a very common pathway that the radicals will go down. Another one is called the homolytic bond cleavage, and that is when radical targets a bond that is generally has a perfect dipole, perfectly covalent, has the same electronegativity, that gives a new radical. So over here, that's an example of this. This radical targeted this bond and caused it to homolytically cleave, giving a new radical and our desired product. And one that's common to termination is the combination, and that's when the radicals combine with other radicals to give a non-radical. Okay, so let's look at another pretty common reaction that we'll use. So here we have this sort of alkene, and we want to generate this. So this reaction is actually called allylic bromination, because this is the allylic position, and it's receiving the bromine. To do this, we use a very special molecule called N-bromosuccinimide, which looks like this. You should know the structure of this and the name of this because it might show up on your exam. So if you have the N-bromosuccinimide and you have trace acid when you're using it, you'll undergo the following reaction and generate succinimide, which you also need to know for your exam, and the bromine. So the reason I've been told why we do this, I'm not entirely sure if it's true, but I'll just tell you what I've been told, is that we don't want too much Br radical, because if we have too much Br radical, we'll have lost our selectivity in creating a lot of our products. So we want to keep the Br radical concentration low. As a result, once we have a low Br concentration, we use the light to generate the Br radicals. Once we do that, we do the exact same thing we did last time. So here, the Br radical is going to attack at the allylic position and generate the allylic radical, and also, I forgot to put here, the BRH, or the HBr. So again, this previous step was our initiation. Over here, this is a propagation step, and is going through the H-atom abstraction pathway. Remember, whenever you do the H-atom abstraction, if you're trying to draw the mechanism for your major product, you want to generate the radical that is most stable. Here, that's going to be at this position. You don't really have a lot of choice because this is, well, you don't really like vinyl radicals. Those are pretty bad. A radical in a double bond is not great. So you really want to generate this allylic radical here. And the reason why allylic radicals are pretty good is because you can undergo radical resonance. So this will be in equilibrium, oh, sorry, not equilibrium, but this will be in resonance with this. So if you draw the fishhooks like this, that goes there, that goes there, that goes there. This will generate the new pi bond, and then since this is homolytic cleaving, you'll get a radical here on the left. Okay, now assuming that we've done that, we have our allylic radical substrate, and it will do the exact same thing as last time, which is encourage that homolytic bond cleavage of the other Br2 molecules that are present. What this will do is it will generate our desired product, but remember we had a radical here and we're generating a radical here, so this is still a propagation step. So desired product was made and another Br dot was created, and that Br dot will go back to this propagation step and do the H-atom abstraction. Okay, so we won't look at the termination steps there because there's many of them. Okay, so the last kind of radical mechanism that you're responsible for is a little bit different than the other two mechanisms. So here we're using hydrobromic acid in the presence of a peroxide. So the peroxide has the very special trait, just as the Br2 did, in having this very perfectly covalent bond with the same electronegativity between these two substituents. So if you have the ultraviolet light, you can encourage a homolytic bond cleavage to occur, and this will be your initiation step because now you've created your radicals, you've introduced radicals into your system. Just as before, the peroxide, well, the first step that we'll have is an H-atom abstraction. This one's a little bit weird because we're not actually doing it on the substrate yet, but this is the step required to start the propagation. So again, you had a radical over here, now you have a radical over here. We've once again generated Br dot, except this time, again, once it attaches to our substrate, something very strange is going to happen. So take a look at what's going on here. Before, we saw H-atom abstraction. here we're seeing a new type of, I guess, reaction step. So this is what we call a pi addition. So instead of attacking the allylic position and doing the H atom abstraction here, what you have is the radical directly attacking the double bond. So that will cause this to homolytically cleave, putting a radical here and a radical here used to form the bond with the Br radical. And over here you will generate this. So note, when attacking the pi bond, you want to make most stable radical. So we could attack on this side or this side. If we attack on the right hand side, we generate this radical here, which is secondary. If we attacked over here with the Br, we'd have the Br on the secondary, and we'd have a primary radical, which is relatively unstable. So you want to generate the most stable radical intermediate. So what you're going to do is do the radical attack on this side over here. Okay, and then we pretty much go back to business as usual. Once we generate this, it's again pretty strange. The substrate does the H atom abstraction on HBr. Remember, the reagent you're using here is not Br2, it's HBr. Br2 would have undergone the, I guess, homolytic bond cleavage here, but instead you wanted the peroxide to do that. Okay, now once you've done that, this will undergo the H atom abstraction, and you will get this. You will also, of course, get another bromine radical. So let me go copy that. Now that you have another bromine radical, it could once again go back up this step and do the pi addition attack on the substrate. So again, this is a propagation step, not a termination step. Again, we're not going to draw the termination steps. You'll notice that we started with this as our reactant and this was our product. You'll notice the bromine got added to the less substituted side, or the primary side of the double bond, and the H got added to the secondary carbon. So if you remember back to your electrophilic additions, this is what we call anti-Markovnikov addition of HBr. So if you want to add bromine to the less substituted, less substituted side of a double bond, you can use the hydrobromic acid in the presence of peroxides and light. Okay, so here are a few problems to try. I want you to predict the product of each of these reactions. And the hint is that, remember, Br2 and NBS undergo H atom abstraction. That's the important step. But hydrobromic acid in the presence of peroxide undergoes the pi addition. Okay, so pause the video and predict the products of this reaction. Okay, I'm going to assume you give it a try. So again, when we're doing a radical reaction with Br2, we're going to do an H atom abstraction and try to generate the most stable radical, which is going to be at this location. So once we generate that most stable radical, it is going to, well, acquire the bromine there by attacking the Br-Br bond. Okay, over here with the peroxide, remember that's going to be the anti-Markovnikov addition to this double bond, so we'll expect to see the bromine here. Remember, the Br dot is going to attack the double bond to generate the more stable radical. So the Br dot will attack here, generating the tertiary radical, which will then undergo the H atom abstraction. And over here with the MBS, again, you're looking for H atom abstraction, and because you got this double bond, the H atom abstraction is going to happen at the allylic position. So you have a few spots that are allylic, such as these, but you'll notice that when you form the radical at any of these locations, or particularly this location, or actually more like this location, what you could have is that radical resonance that will give you a tertiary radical at this location. As a result, that will be the most stable radical, so that will lead to your major product. Okay, let's completely switch, I guess, our mindset and try to predict bromination product yields. So the problem that we're given this molecule, and we're given a lot of flavor text information. So here you see a bunch of stuff. We're given the name of the compound, and we're told, the only thing that's really important here, you could pause the video and read the rest, but we're told the relative selectivity of the Br2. So it's in the order of the substitution of the bonds. So you'll see it's 1 to 2 to 5. That means it has the highest selectivity for the tertiary CH bonds. So the way you attempt this problem is, first you want to find the tertiary CH bonds, the secondary CH bonds, and the primary CH bonds. Because remember, when you're using Br2, any of those bonds can undergo the H atom abstraction. Okay? Actually, just to be, I guess, technically correct, we're not doing bromination, we're doing chlorination. I think from reading over here. Yeah, monochloration product. So the reason we're doing monochloration is because that goes back up to here. Br has high selectivity for the most stable radical, but Cl has relatively low selectivity. It'll select, as you see here, 1, 2, 5. 5 means it has the highest selection for the tertiary CH bonds, but you see that it actually also has some selectivity for the primary and secondaries. So the tertiary, you could form, well, you could see these two CH bonds. They're located on the ring. For the secondary, you'll notice these two CH bonds, and the reason why they're different colors is because after the H atom abstraction and the subsequent, I guess, radical reaction, you will have one of these CH bonds replaced by a chlorine. Now, if you replace one of these with a chlorine or the other with a chlorine, what you'll see is that you will get the same name. That's why they have the same color. So if you get the same name, you'll actually have the exact same molecule, right? And the way to tell if you're going to get the same, I guess, thing is if these are symmetric. If you're able to imagine the H&MR spectrum and these giving you the same signal, then they're going to give you the same, I guess, common name or IUPAC name when you name it. They're going, in fact, to be the same molecule when you do that replacement. Over here, if one of these CH bonds up here in the green are replaced, that's going to have a different name than if we replace one of these blue CH bonds down here. If you don't really get it yet, you'll understand soon. The last example, when we're doing primary, there's actually a bunch of them. They're all here in pink. So any of these methyl groups over here are going to be primary and have those CH bonds located around like that. Okay, so the next thing you're going to want to do is you're going to want to find, I guess, the total possible yield. So this is our selectivity over here, our ratio. The total is going to be the number of each of these times its relative rate. So if the tertiary has a relative rate of 5, then we're going to need to do the 2 tertiary CH bonds times 5 here. Over here we have a total of 6 secondary CHs, so it's going to be 6 times 2, which is its relative rate. And over here we have 18 primary CHs times a 1, which is its relative rate, which will equal 40. You'll see what we do with this 40 in just a second. So suppose we did the chloration or the monochloration on the molecule and we generated this. So this was our tertiary, right? There were two of these guys. What that means is that the proportion of this product that's going to happen is the two of these guys times their relative rate, which is going to be 10, and we know the outcome of all of them is 40. There's 40 different possible, I guess, things that could happen. So 10 out of 40 are going to result in this. And notice that if we put the Cl here and the H here, that is actually going to be the exact same molecule. Likewise, if we do the same sort of thing on the CH bonds that are primary, you see that there's 18 possibilities here times the relative rate of 1. So what that means is the relative yield will be 18 out of 40 of your possible products are going to be this. Notice if I put an H here and replace any of these with a Cl, you'll have the same IUPAC name, and they are equivalent by H and MR, so they're actually the same molecule. Okay, if I replace one of these light green ones with a chlorine, they are the two secondary CHs I have, so it's going to be 2 times their relative rate, which is, again, 2. So 4 of the 40 possibilities will be that molecule. And then lastly, I have these 4 blue CH bonds over here that are secondary. So it's going to be 4 times 2, the relative rate, which gives 8 out of 40. Note that all of these must add up to 40 because that's what we got from the total. Okay, that might have been a bit confusing, but you really learn how to do it by doing examples. So pause the video and try this problem. Okay, so we're going to do the exact same thing we did last time. So first, identify the primary CH bonds. Next, you're going to want to identify the secondary CH bonds. And then lastly, you're going to want to identify the tertiary CH bonds. And you want to identify them by, if I make one of them chlorine, will they have the same IUPAC name or H&MR spectrum, or they won't? So if I replace these two over here, that'll be a different molecule, but if I replace any of these, because of the symmetry, they will give me the same IUPAC name. This time, our relative rates are told to us as this. So again, the first thing we want to do is we want to find the total. You see that there's 12 primary CH bonds times the relative rate of 1. There are 6 secondary CH bonds times the relative rate of 4, and there are 2 tertiary CH bonds times the relative rate of 7. You add those all up and you get 50. Next thing you need to do is what we did last time, is replace one of those CH bonds in the primary with a chlorine, and you'll see that you have 12 possibilities with a relative rate of 1. So 12 out of your 50 products will be represented by this. For the tertiary, there are 2 tertiary CH bonds and the relative rate is 7. So 14 out of your 40 products will look like this. And then for your secondaries, you need to split them up into this blue and green because they'll give 2 different IUPAC names or 2 different H&MR spectrums. So again, you have 2 of these secondary CH bonds times the relative rate of 4, which will give you 8 out of 50, and the other one, 4 times 4, will give you 16 out of 50. And all these, once again, must add up to 50. Okay, so what is the takeaway? Well, you should understand the initiation, propagation, and termination. In terms of radicals, you should understand radical stability. Going through pi bond resonance, you should understand the ways that radicals can react, such as hydrogen abstraction, homolytic bond cleavage, combination, or don't forget about pi addition. You should understand that the peroxide mechanism will go through a pi addition step, and the NBS or BR2 in light examples will instead undergo the H atom abstraction. And then lastly, you should be able to figure out the products of monochloration and their relative yields based on a given relative rate selectivity.